I am unmuted. All right. Hello, everyone. Welcome to this meeting of the Warren Astronomical Society. I am the president, Bob Tremblay. Turn down so I can actually. Oh, hello. Oh, testing. Microphone. Oh, lectern mic. Testing, testing, testing. Testing, testing. What the heck? Testing,
Yeah,
testing.
I'm hearing you, Bob.
No, the lectern mic. So there we go. The audience can. There we go. Guys, hear me now? Can you
Yes. Yep.
can you hear me now? Okay, okay. So welcome to this meeting of the Warren Astronomical Society. I'm the president, Bob Tremblay. So do we have any first time attendees here tonight? Well, okay, let's do this. Okay, we know. You're not a first timer. Hmm? Jeez, oh Pete. So so yeah, we have an observatory at Walcott Mill Metro Park. If you haven't been there, it's very cool. Every fourth Saturday of the month, we do an open house, and sometimes we have telescopes out on the field. It's very, very cool. So you can renew your membership at lunch at the snack break with David here. If you'd like a WAS lanyard, get with us too. So if let's do a roll call. We usually go to up and down the rank, giving our names. So I'm Bob Tremblay. Hi.
I'm third meeting here. I'm here. And that's. I'm Brandon Nagel, Charles Pratt, I'm secretary. I'm up for my third meeting.
Awesome.
That's the registered member.
Mark? Oh, okay. Mark can't do. Hi there. All right. Hi, everyone. All right. So, I have not received any information on Marty Kuntz's memorial service yet, so we will get an email out as soon as we get something on that. There are three calendars left for the low price of 15. Can we give a discount now since it's halfway through the year? These are astrophoto calendars with pictures by the members. They're very, very cool. So pick them up while they last. And where's my cursor? There we go. Okay. So Lost Wearables are available. You can see what's available. You can see what's available in our newsletter. You can order them from Mark Kedzier here. Astronomy at the Beach is going to be held at Mayberry State Park, west of Northville this year, because Island Lake State Park will be closed due to construction. We are looking at doing highlighting light pollution because it's close to Northville and the light pollution is going to be pretty bad. So I've contacted Sally. How do you pronounce her last name? Oi, we. Oi, yeah, I've contacted her. She'd be interested in speaking, so we started that ball rolling. If you'd be interested in helping put on astronomy at the beach, black meetings are held the second Monday of every month. So officers reports. Geez, I didn't actually write anything because I was spending all the time doing astronomy and the news stuff. So I'm still showing every chance I get to show my 4-year-old granddaughter a picture of the eclipse, I do. Remember seeing that? Because I desperately want her to remember seeing that. Probably, but yeah, she was there. So Dale Parton, our first vice president, he's going to tell you we want presentations.
How did you guess? Seriously, I'm always open to new people or not so new people who would be interested in giving a presentation. You don't have to have it ready. We're booked up through early October, so you'd have plenty of time. But let me know if you have something in mind, okay? I'd be interested to hear from you, either a long or a short presentation. Thank you.
Yeah, making a presentation on your own, you can learn a whole lot. I mean, that exoplanet one I did just recently, which I'm going to have to update every time I do it now. But um, yeah, I learned a whole lot doing that one, so it's really cool. Um, Riyadh, are you online? Oh,
Yes,
out
yes, I am.
observatory.
Yes, thank you, Bob. Hello, everyone. We had our open house on April 27th. We started about 7 p.m. We had roughly about 50 people, including visitors, club members, and scouts. We used the 8-inch refractor. The sky cleared up after a little while when we got there. And we got to see a few deep sky objects. We looked at some double stars. We looked at Betelgeuse. So we spent the night hopping around from object to object. Unfortunately, at this time of the year, or right now, at least this year, the planets are close to the sun. Either they're close to the sunset or just before dawn. And the moon wasn't available either, but we got to see some some galaxies, which was quite a challenge for new people who haven't looked through it, even a telescope before. But that's what we had to look at. It was a lot of fun, actually. And we also had a bunch of scopes set up outside. People were doing their own thing, doing astrophotography outside the observatory and looking at objects. So we stayed out till about 11:30, and when we closed. Next open house is going to be May 25th, so hopefully we'll have a lot of people showing up. We've also been doing some open houses for scouts. So last month on the 20th, I had a number of scouts that showed up and gave them a talk. And then also this last Saturday, we had a camporee out there. Now there were supposed to be about 80 scouts, but I think we only saw about maybe 40 or 50 of them, something like that. Anyways, they kept us busy for a while. It was also enjoyable to talk to the kids and show them the different telescopes and answer their questions on observing. So hopefully we'll see everybody out on the 25th, next open house. Come on out, you'll have a lot of fun, and especially if you have clear skies, you'll enjoy it. Thank you.
All right, thanks. I'm going to try and get the speak. I'm trying to get the speaker. Yep, yep, yep. The Stargate Observatory. Jeff, you want to come up and tell them about since well, let's come on up and tell them about that. I'm going to try to get the speaker working here. I know we are.
Do this. My report is on a sticky note that I did underneath. This is out at the observatory right now. You see the building behind him? That is the Stargate Observatory, and it's a beautiful. I think it's a sunrise. I think he's out there good morning. We also have a flyer. All the info is on that banner to the left of me. People can't see it. But it's out mid-Macomb, 29 Royal Planetary. We have an 8-inch refractor. Using sort of a 22-inch refractor in our cell. We have a bunch of the scopes. People bring their scopes. It's a grand old time. Should I do what's my job? I already said it.
Yeah.
Okay. If you'd like to do outreach with me, send me an email or see me at the break. I'm just looking for new people and new opportunities to get people outreach. But for the things that happened in the past, Alberta is in, looks like Aruba. No, there it is, yeah. Beautiful Aruba right now. He was on Channel 7 talking about the eclipse beforehand. Ken, they're in the middle of the room. Do you know what channel you were on? Okay, he got interviewed by the news. He was with what's that? Oh, yeah, it's gone. With his wife. Yes, but you were there. And Robert all and friendly with it. And the company, they're inundated. People look at the sun. And it's not even a bigger fun for them. He was down in Dayton at the Air Museum with like 10,000 of his closest friends and family. On the 13th, Riyadh had scouts at Stargate, and Bob and I were down at Belle Isle doing statewide astronomy night. That was a pretty fun event. Future stuff. So the next big one is the Selfridge Open House / Air Show. That's June 8th and 9th. It is free admission. There's going to be like tens of thousands of people over the 2 days. It's going to be a huge event. We've been we're definitely not the there's fighters in this flying. No one's going to be paying attention to us, but it's going to be a good time. Bob has promised to run a table and bring in the spaceship. If you want to help Bob or I, also let me know. Yes. Thunderbirds, not Blue Angels. Yeah. 3.5 hours. And then way out in August, there's a library that wants just like a basic astronomy. I'm going to do it if no one else volunteers, but if you would like to volunteer, please do. That is all I have for outreach. Take it away, Bob.
I'm not sure if I got the speaker working right here. This thing is being finicky tonight. So let's see. I'll turn this thing off. Say, Riyadh, can you just say something? Give me a test.
Okay, can you hear me right now? Is that too loud?
We didn't get thanks. We didn't get the tech working tonight. Sorry. Okay. David. Up here. This is our treasurer, David Bransky. How are you doing?
All right, so in our treasury account, we have $25,399 and a whopping 43 cents. We did have a credit card bill last month, but that was paid for. In case you're wondering what was on there, there's a box, there's a briefcase. And we made a reservation at the banquet hall at the Ukrainian Village. And our next bill coming up is to pay for that for Zoom. That's for $159. And our tax exemption has now been updated, so we're all set there. And we have a couple calendars left.
Thanks, David. Charlie, secretary. What do you got going on? David, I am just going to hold this mic down to the laptop when you speak because I am not coming through the overhead speakers here. So we'll get you.
All right. Good evening. I'm Charlie Strackbine, and I'm the secretary of this group. I'll keep this very brief. The April meeting minutes can be found in the May issue of the WASP. Thank you.
Thank you. That was really simple. Thanks. All right. We've done outreach already. We've done that. All right. Publications. Natalia is home ill. Dave was here and he can tell you that the WASP is out. Or the WASP is out. We have a newsletter online available on our website. This guy is one that's been doing it for years and it won an award from the Astronomical League. What was it, 2 years ago now? Yeah, so and it's very nicely laid out. Lots of and like take you a long time to read it. Really, really cool. So it's on our website, warrenastro.org. You can find it under newsletter. So if you need to contact the board for any reason, you can contact us at board@warrenastro.org. So astronomy in the news, really quick. We have 5,616 confirmed exoplanets. That's up 4 from 2 weeks ago at the Macomb meeting. We have 7,138 candidates, and that is unchanged, which I am really surprised because I've seen that number go up practically every day. An interesting piece of news on the NASA Exoplanet Archive was that exoplanet TOI 4633c was discovered by citizen scientists using data from NASA's Transiting Exoplanet Survey Satellite TESS They discovered it. Since they discovered it, they got to name it. They named it Percival after the father of Albus Dumbledore, the headmaster of Hogwarts in the Harry Potter books. Percival appears to be have the most elongated orbit of its planetary category, namely Neptune-like planets. And the graphic on the side shows the star with a couple other planets. This one orbit is really elongated, so it's bizarre. On April 22, I love this story. This Scott Manley did something on this on YouTube. Voyager 1 is now sending data back to Earth for the first time in 5 months. The Voyager team determined that the cause of the problem was that 3% of the flight data system's memory was corrupted. A single chip responsible for storing part of the system's memory, including some of the computer software code, was not working properly, likely a cosmic ray hit. Since there's no way to repair that chip, the team opted to store the affected code from the chip elsewhere in the system's memory. While they couldn't pinpoint a location large enough to store all the code, they were able to divide the code into sections and store it in different spots within the flight data system. To make this plan work, they needed to adjust those code sections to ensure that they all functioned as a whole. So this amazing story is an outside the box engineering analysis and repair. It's just amazing. What also amazes me is that there are people around that can understand the inner workings of Voyager 1's 46-plus-year-old flight data system, and they're able to implement this fix. That is just kudos to NASA. That is just an amazing story. So, David Levy, I am going to put the microphone down on this laptop, and Dr.
Well,
David
thank you.
Levy.
Thank you very, very much. I'm not going to be able to spend too much more time here, but I did want to come in for the opening of your wonderful monthly meeting. I'm certain most of you got to see a magnificent eclipse on April 8th. We were completely clouded out, as you know, if you read the article. We did get a number of views of the incoming partial, and then as the temperature started to drop like a rock, we were pretty sure we weren't going to get any totality. And the group asked if instead of just seeing totality, if I could quote a poem. So I thought if Shakespeare were here, he would have said from Macbeth, "By the clock 'tis day, and yet dark night strangles the traveling lamp. Is it the night's predominance or the day's shame, that darkness is the face of earth and tomb, when living light should kiss it?" And I quoted something else as well. 20 seconds later, there's the corona in all its magnificence. It was the most magnificent eclipse I've ever seen. And then it was over. Only it wasn't, because we got to see the most amazing view of Bailey's beads, which incidentally are named after Francis Bailey, but even though Edmund Halley of comet fame was the one that first described them about 120 years earlier. So for my formal quote tonight, I'm going to read again from William Shakespeare, his sonnet 14. "Not from the stars do I my judgment pluck, and yet methinks I have astronomy, but not to tell of good or evil luck, of plagues, of dearths, of seasons' quality, nor can I fortune to brief minutes tell, pointing to each his thunder, rain, and wind, or say with princes if it shall go well, I oft predict that I in heaven find. But from thine eyes my knowledge I derive, and constant stars, in them I reach such heart, as truth and beauty shall together thrive, if from thyself to store thou wouldst convert, or else of thee this I prognosticate, thy end in truths and beauties, doom and date." Thank you very much. Enjoy your meeting. Back to you, Bob.
Thank you, David. Whoa, let's lower that again. All right. For those who don't know in our audience, Dr. David Levy is an astronomer. He considers himself an amateur astronomer, but way back in, was it 1994, the Shoemakers discovered a comet that plowed into Jupiter, and it was one of the most titanic explosions ever witnessed in the solar system, and we all watched it happen. Well, I've several of us here watched it happen. Dating myself there. So that was 1993. It was discovered. 94 it impacted, and Hubble caught pictures of it and several animations of it. Very, very cool. So in solar news, there was an X 4.5 class solar flare today, causing deep shortwave blackout around the Indian Ocean. This marks the fourth X-ray flare since May 3rd. Well, actually, that's probably wrong because as I was standing here setting this up, I got some flare notifications. So the SDO, there's a lot of sunspots right now. You could probably actually see them with the solar glasses we down here for free. So Riyadh, you got any double star reports?
Well, we looked at a few double stars, like I said, this last open house. One of them was Castor, and that was absolutely amazing. Some of the kids that were looking at it, at first they thought it was one star, but when I told them to pay attention and see if they could see the split between two stars, yeah, then they were surprised that it actually is two stars. Yeah, so we looked at a few of them like that, and yeah, they were kind of fun.
Thank you, Riyadh. Oops. Ooh, there we go. All right. So if anyone wants to start a special interest group, be it radio astronomy, computer technology, education, which I should really do, light pollution, podcasting, go ahead. Get with the board. So let us know you're going to do it, and you can do a presentation about it. So do we have any astro photos or observing reports?
Point out real quick, Rion on the top row there, he's not at some fancy NASA center. He's now moved into the observatory, and that's our telescope. If you want to look into that.
So Jeff is prognosticating about Riyadh's background picture being our observatory's telescope. So any observing reports? So what do you got? What do you got, Gary? Come on up.
That's right. No, they can't hear me from here. No, they can't. Oh, the virtuals, right?
What is going on?
Virtuals.
Attenzione, all virtualis out there, right? I rise to report that in the middle of an observation of DV Cygni 2 mornings ago, a high fog formed and took it away from me. And that is my sterling observing report. But more will be said under general announcements if the chairman is good enough to ask for them. I have momentous news that are not observing reports. But remember this, I'm still the first greatest observer in Michigan.
Momentous news. Not just exciting, momentous. Awesome. All right. So if we don't have any other observing reports or anything, you guys are up. Let's get your presentation up here.
I'm up. Oh. What's this?
You
Short speaker. Short speaker. Oh, speaker. Sorry. I forget that stuff. Yeah.
okay, moving this over to here.
It's not like this. This is practical art.
You want? Oh, wait, no. Oh, what presenter notes on here?
Yep.
Slideshow. Presenter view. All right. Well, I'll tell you what. I'm gonna put the presentation over here, and the presenter view is sitting here, so you can use the mouse to go through your slides. But let's make sure it works right. What is going on? That There it is. All right. Yeah, that's working. Next. Okay, good. You just click in the picture. Click on the picture. Okay.
I would just like to acknowledge John Dumar, extraordinary astronomer who got into this how many years ago?
Five, no, 7.
7 years ago. He became an expert on studying the moons of Jupiter, measured their orbits with extreme precision, and managed to entice some of his high school physics students to get into this not crazy thing we're into. John.
All right.
Zoom. Where's the zoom? Where is it? Hmm?
They, they have note cards. They don't need the notes on here at all.
Okay, well. All right, I will cancel that. That. What? Doing this.
No, that's all right. It's cool.
I love this. All right, share screen. Here, going to share that. Share. All right, so if you're over here. All right, you can click on that now. In the middle of that. It's presenting over there. Oh, you can just use this. You can use the mouse scroll wheel. Just scroll it down.
Okay. So I want to thank the Warren Astronomical Society for letting us to present our day at the eclipse. So I asked 3 of my students to present their day. Bianca, Ketty, she's a senior at Luther North. She is a played track and cross country. She's on the National Honor Society. She's one of our 5 valedictorians this year. And Bianca plans on attending Detroit Mercy College and become a mechanical engineer. Brandon, another senior at Luther North, another one of our valedictorians, played soccer and basketball, enjoys reading and playing chess. Brandon plans on attending Michigan Tech and plans on studying mechanical engineering of all things. Josh, Brandon's brother, obviously, is also another valedictorian. And he played soccer and basketball. He enjoys reading and playing chess, amazingly, like his brother, and plans on attending Michigan Tech and becoming a mechanical engineer. So I'll let them present the day at the eclipse that I allow them. Took them all down to go see. Right.
Hello. Okay, so to start the trip off, we met at our high school at 5 a.m. We met we met there that early because we thought there'd be a lot of people getting down there, and we didn't want factors like traffic or factors like construction preventing us from getting there to see the eclipse. So we left at 5 a.m. We met at 5 a.m. to go and drive down to Ohio to go see the eclipse. We brought stuff such as chairs, blankets, Mr. Dumar brought his telescope so that we can look through that to see the eclipse. We brought games, lunch. We had lunch and dinner because we thought we'd be there for a while. And after that, we split into our separate groups. We went with 12 kids. 6 of us were juniors and 6 of us were seniors. So our juniors went with one van and our seniors went in another van. So after that, we hit the road and started going down there. So traveling there, we were in the car for about an hour. And during that time, it was early in the morning. So we, most of the time, kind of slept. But while we were up, we talked about various books that we were reading, like games, and talked about different stuff that was going on at the time, talking about how we were excited to see the eclipse. So about an hour and a half before we got to the place where we were going, which was Modern National Park, we stopped at McDonald's to stretch our legs, to just get out of the car because we were kind of tired from sitting for an hour and a half. So then after that, we reached Modern National Park, or sorry, Modern Metro Park. That's the park right here. So once we got there, it was about what time? I think it was about 8-ish that we got there. But when we got there, there was only pavilion. There wasn't much things to do because we got there pretty early. There was also not a bathroom, so we decided that this is not that great of a place to go. So thankfully, Mr. Dumar plans another national metro park to go to. So after that, we went to Ottawa Metro Park. This park had a lot more activities to do. They had a big lake, they had playground to go play on, places to walk around. So once we arrived here, we hung out there until the eclipse. Okay. Right. So as you said, we got there like really early because we were expecting to take a lot longer to get there. So we had like a ton of time to kill. So since we're all kind of kids at heart, we decided to go to the playground first to hang out with all the juniors who also went there. Then after we kind of got bored of that, we went to a no, we went back to Mr. Dumar's telescope and we saw I think there's 4 sunspots, and then Mr. Dumar kind of explained to us like why the sunspots were formed, which was really interesting to see. Then after that, we went to a nearby pavilion to like kind of have snacks and play games and just kind of like waste some time while we're waiting for the actual eclipse to occur. Then after that, we kind of got bored hanging out there, so we went to kind of go walk around to see what else they had there. We found this one like dock, and we kind of just like stayed there for a little bit, like admired all the like beauty of like the area. Because as you said before, there's a huge lake, and we could like it was like nice to see like the sun off the water and all that. So after that, we were pretty hungry, so we went back to the van and kind of just like sat around and we had lunch and we had like two of like we had a calculus worksheet and a like eclipse worksheet. On the eclipse worksheet, we learned about the umbra and we also got this like cereal box and like had a pinhole in one side and looked through the other side of the box and we're able to see the sunlight kind of reflected on the box. And we use this like during the eclipse to see the moon kind of going over the sun, which was really cool that you didn't actually need glasses. You can kind of just see the reflection. But it was also really cool to see everything kind of like flipped in the box than it actually was in the sky, which was, and then on the worksheet, we also found out why all that also happened. So then since we had 1 hour left, no, since we had a half an hour left, we decided to just go for a walk around the entire lake. However, this is kind of problematic once we got halfway across and we realized we only had like 10 minutes left. So we either had to like go back or like really hurry up. So we decided to run about like half a mile to try to get back on time. And we got back with like probably 5 minutes left. And then after that, we kind of turned all our chairs to face where the eclipse was going to happen. And Mr. Dumar kind of adjusted his telescope to like be pointing where the eclipse exactly was. And then the eclipse began. And then these are a bunch of pictures of us throughout the day. The picture in the center is all of the group of us. The picture of the left is us hanging around the dock. And on the right is us kind of having our lunch and doing our worksheets. So then for the eclipse, we took these pictures through the telescope. However, when we actually saw it with the actual glasses, it was going, the moon was coming from the bottom right to the top left because the telescope kind of mirrored everything. So it appeared to be going from the bottom left to the top right. But then as we were waiting for the eclipse to happen, we kind of got the glasses so we could see it ourselves. And Mr. Dumar got us this lens thing that we can put on our phone so we could take like clear pictures through our phones. So that was really cool to get a bunch of pictures as the sun kind of like progressively went away behind the moon. And then we saw that it was kind of getting darker and everything was kind of getting colder. And it was cool to kind of see the contrast between like right in the day, like to right before the eclipse happened. Like I just think it's really interesting that it got like completely dark and really cool that it happened. And then we just waited for the total eclipse.
So at the moment of totality, we all had our glasses on and we're looking, and then right when the moon completely covered the sun, you could just hear everybody in the park like in awe, hearing, we all were cheering, and then we all gathered around Mr. Dumar's telescope, and then we looked through it, and one of our classmates got a really cool picture. Oh, there's of these two. Oh, we could see the corona really clearly, and that one's pretty cool too. We all Oh, and you could see the solar prominences, the red dots, which was really cool. So during the moment of totality, we all were just in awe. And in my opinion, the pictures just don't do it justice of how just amazing it was to see the corona so clearly. And it was just amazing to be able to be there and experience it in person, especially since, I mean, we're high schoolers, so it was just amazing to have the experience to be there and witness it ourselves. And I'm really thankful for Mr. Dumar that he took us there to see it, because not many people got to see it in the line of totality like we did. So it was really amazing and an amazing experience. Here's a few pictures of us. Oh, and when it was the moment of totality, it got significantly darker and a lot like cooler. There's Mr. Dumar's telescope. There's us all looking at the sun, and here's the group picture. But yeah, it was an amazing experience. I'm really thankful we went, and especially for us three, because we all are interested in going into a space-related career. So it was just an amazing experience to be able to be there and experience it, because we're all interested in that, and we're all want to go into a space-related career. So it was just amazing to be able to see that in high school, especially. So I'm just really thankful for Mr. Dumar that he was able to take us, and it was a blessing to be able to go.
Right after totality, did you happen to see the shadow bands up around?
Really?
Waves. Shadow waves, like you see waves in a pond. They were kind of on the ground. It was really weird.
We were looking for them, but we didn't really. Yeah. Yeah. We didn't really hear any birds chirping either. We're supposed to be birds, like the birds. You could hear them, but we didn't. I didn't really.
The crickets.
The crickets? No, I didn't really hear.
Yeah, there were too many people screaming where I was. So you planning on going to the next one in 20 years?
Probably.
You guys ask when's the next one?
Yeah.
Everybody.
We'll meet up in 20 years and go again.
Isn't the next one in like Montana or something in 20 years?
Yeah, it's Wednesday goes and the Arctic circles and yeah. Once you want to go 2026 and Iceland, it's in Alberta.
Where is that exactly? Like what country?
Alberta. Oh, that's good. That's good to have a unique. This was the most perfect.
Yeah.
I'm curious if you could like try to put into words how it stacked up against what you were expecting, because I'm assuming you saw pictures of previous ones. How did it compare to what you had in your mind?
It was a lot better than I thought because I like pictures, you can kind of see a picture and go, okay, there's a moon in front of the sun. But when you actually see how slowly it moves over and in that moment, for me, it was just like you just, I can't really put it into words. It was just Yeah.
Yeah, I just think it was like one thing that I thought was really cool about it is just seeing how perfect everything lined up. Like people were able to predict that all this stuff was going to happen like many, many years ago, and everything happened the second that they thought it would happen. So I just think it's cool how like everything's so perfect and like even the pictures, like the edges of the moon in person was just so much more clear than like even that picture there. I think's a bit like blurry compared to what it was in person. Like it was so just like everything was exactly how it should be. I just thought that was really interesting.
I have the same feeling. I looked at it and the first thing I thought was like I can't put into words how beautiful it is and just like the majesty of it. And then the pictures like in person it's like glorious. You're thinking like the world's gonna end or something. It's amazing.
All right, well, let's see what time it is. 7:41. So we usually take about a 20-minute break right now. So why don't we reconvene at 8 o'clock straight up? They give us a 20-minute bio and snack break. See you in 20 minutes. And stop sharing. And mute. I miss Brian. All right, 8 o'clock. Everybody, let's start. Take your seats, please. All right, so welcome back to the Warren Astronomical Society, and now we're going for our long presentation. Take it away, Dale.
Well, this is our, as you just heard, our main presentation for tonight. Jeff MacLeod is well known in this organization. He's previously been our president, the observatory chairman, and now he's dropping things all over the place. He's now our outreach chairman. I was surprised. I don't know how old he was when he decided to start working on a bachelor's degree at Wayne State. Old, he says. He wasn't exactly straight out of high school. 31. So I admire him for doing that and getting a double major in physics and astronomy. 2 for the price of 2. So, and now he works for some aerospace company simulating missiles. Sounds rather exotic. And he's been working on this strange spacecraft. And that's what he's here to talk about tonight. Take it away, Jeff.
It's up? Okay. So I need to finish this real quick. Who here knows almost nothing about the Apollo program? Please raise your hand. You are the most important people in the room to me. So I got 3 back there, 1 there. You guys represent like people that are high up in the government and the military. Okay, now who knows a bit about Apollo? Okay, most of us. You guys are contractors for the program. And who knows everything about Apollo? Okay, you guys are program managers, NASA management. Good luck trying to convince the top brass what you want and what you think should be done. Because what I've done here is I've pulled a little bit of a switcheroo. The presentation is not building an Apollo mission from scratch. I thought that the real title might scare you, so I lied. My apologies. We are about to take a trip back to 1962. Okay, we're about a year after Kennedy's "We Choose to Go to the Moon" speech. We've had 3 launches of the Mercury program, 2 suborbital and 1 orbital. We've spent less than 6 hours in space today. Okay? Gemini is on its way, but it's not flown yet. I don't even think we have a crew for it yet. And Apollo has been named, so that's all we know about Apollo. And so what I'm asking you guys to do that I know this stuff, clear your minds. Okay, you don't know this stuff because it hasn't happened yet. Okay? We're here to make a decision. We need to figure out how we're going to make Kennedy's dream a reality. And lastly, this report is not historical. This is my number crunching because this hasn't happened yet. There's no books to look into. Okay, so are we ready for the real precision? This was generated by AI. It did a pretty good job, but as you can see, it leaves some wanting. This is another. All right, Bob, it's not working now. Can I click? To what? There's two of them open now. Okay. So there's another AI. This is the real presentation. Can you see what we're worried about here? Mid-year council meeting, 1962. Feasibility of new permission proposals, early analysis. I'm going to need to get into character to do this. If you'll excuse me a moment. Okay. Well, we've got some journalists, I don't know why they asked me to give this presentation. Some of you may know, I don't work on the Apollo. I'm a Gemini guy. Okay, I'm going to be giving this presentation. Sometimes refer to as gentlemen. I can't see anything without these glasses. I brought a calculator. All right. Hold on, it's here somewhere. Your blue size IBM. Ah. Still? All right. Sorry, I can't do anything without a cigarette. And then we'll be using these very expertly crafted models to talk about some of the stuff that we're doing here. Okay. Ready? Remember, 1962. If you guys are virtual, wait, I'm afraid to move this. I'm really bright on this thing. Okay. Let me tell you guys, we need to get this done. All right. You guys in the ether space, I don't know how to handle you because this technology doesn't exist. So I don't really believe that someone brought in some sort of fancy channel 2 camera and they're beaming me all over the country. Okay. So if we want to get to the moon, we have to do a couple of things. We need to, 1, navigate, 2, guide, and 3, control the spacecraft. Now we do that. These things are all interconnected. Navigation is dependent on infrastructure. Control is dependent on rockets. Guidance dependent on trajectory and maneuvers, and them themselves dependent on rockets and infrastructure. So what do I mean by this? These are 3 distinct things. They get conflated often. Navigation. This is knowing where you are in space. Has nothing to do with where you want to go. It's where are you? How do we determine where we are? We're going to do this with radios. We're going to do this with sextants. We're going to do this with trigonometry. Guidance. Where do we want to go and how are we going to get there? This is the trajectory that we're going to talk about. And finally, control. How do we actually make the spacecraft do the things that we need it to do? That in development is a command service module engine with a human next to it. All right, now to get this done, because it's 1962 and we just got to move fast, we're going to simplify things for you, okay? 1, 2D. I'm flattening the entire universe, so we don't have this extra dimension to deal with. Moon's orbit, circular, good enough. Again, remember, this is not historical. Idealized delta V requirements, okay? We're going to just say that we're going to hit the money in this thing. Assumed rocket tank to fuel ratios. This is important to some calculations that are going to come. I just have to guess. We need a number. Engine. A lot of things are going to be dependent on the performance of the engine. We already have most of these in the works. Okay, the F1 is well on its way. So I'm assuming that we do know that stuff. Some of it can change, but I'm not dealing with air resistance. Not how I was raised. And finally, this is a 2-pronged thing. Yes, I'm using the metric system. Okay, that is wrong. The metric system is wrong. However, for the people out there that do know some of this, this is going to obfuscate things because maybe you've never seen these numbers in metric, so it'll confuse you a little bit. But yeah, sorry, Uncle Sam, metric system. Okay, for you guys, this is what you need to be thinking about as I'm talking about all this stuff. Time. Kennedy said, end of the decade. It's May 1962. We're kind of behind the gun already. Cost. Currently, not infinite. It's going to be infinite maybe in a couple of years, but for right now, we can't just throw money at this problem. Facilities. Can we build it, and can we build it in time? Okay, you might want something, but how you gonna build it? Reliability, complexity, and then finally, Newton's second law. Weight is everything. No fat astronauts. So the first thing we have to do is get into orbit. So this is a very simplified way to calculate the energy required to get into orbit. You have a set speed for an orbit of any altitude. So we calculate the orbit that we want, that has a velocity. We calculate what the orbit would be if you were in orbit at the ground. That is that initial velocity. Then you have a delta V requirement to go from one to the other using a Holman transfer. We add those together. We add 5% for air resistance. I'm saying to go from stationary at the Cape to in orbit above the Earth, 8.43 kilometers per second. Okay, now we've done this. We sent Glenn zipping around, so we know how to do this. We don't know how to do much more than this. All right, this is the big one. Translunar insertion. You guys have some jargon here tonight. This is using this equation here in the upper left, is basically calculating your distance from a body. It's an estimate, Bob. So this is using a two-body solution to give us a approximate. This is not how you do this, okay? If you try to fly to the moon using this kind of system, you will go crazy. That's looking a lot like me when I built this darn thing, okay? We don't want to do this. This is trying to solve a three-body problem using math. You cannot solve a three-body problem. You can only estimate a three-body problem. So what do? We get the most space-age fancy magnetic tape supercomputers to calculate it for us. I tell you, we can calculate one of these trajectories in less than 5 hours, okay? Now, when we simulate, we're taking time steps. We are calculating the force on the spacecraft from the Earth, the force of the spacecraft from the moon, putting those together, converting that to a new velocity, stepping the spacecraft forward in time, and then doing that calculation again and again and again and again and again. And that traces out our trajectory. Now, a couple of things can happen when you leave the Earth. Bottom right, you can hit the moon. Good for some things, bad for others. You can miss the moon and be slung out into a orbit. You can slingshot around the moon and hit the Earth. Good for some things, not for others. And finally, you can swing around the Earth or swing around the moon and just barely miss the Earth, but in a bad, unfavorable direction. This is all based force of gravity, okay? So, we've got some options here. How do we find the right one? We do thousands of trajectories. So this represents tens of thousands of these simulations. The only thing that we have control over is where the moon is when we launch and how fast we launch the rocket. So on the right, or sorry, at the bottom, lunar heading. Where in space is the moon? On the left, going up, our velocity, our transit velocity. So you can see here we have regions where if we go when the moon is at 50 degrees and we don't go very fast, no capture. Okay, this is all based on like what happens after a minimum of like 8 days. There are things that could happen on longer time scales. I'm not concerned. After 8 days, if you ain't captured the moon, something's wrong. You can have, because of that, I have regimes of nothing happening. You can be ejected. You can hit the moon. You can hit the Earth. And then right in between those two bad options is the good option. We'll zoom in a little bit here. Uh-oh, I've lost it again. How? Well, here I am. What if I click? Does that do it? There we go. Still pretty hard to see. Okay. Let's zoom in a little bit more. Okay, now we are down to, what is this? A fifth of a degree in lunar angle and less than 1 meter per second in velocity. That's the whole plot, not just this razor thin return trajectory. Okay, so if you want to hook around the moon and come back to the Earth for free, which I highly recommend, this is what we're going to have to do. Now, fortunately, we don't actually have to hit that burn perfectly. We can do corrective maneuvers, and it's not going to cost us a lot of fuel. We get a beautiful trajectory such as this. Okay? Now, the question I was supposed to ask you, maybe hopefully no one spoiled it. How long does it take to get to the moon? Anybody? 3 days? 4 days? Depends. That's a good answer. If you go fast enough, you can get there in one. This is a little time step dependent, but it's just under 3 days. It's going to take us 2 days and 22 hours to get there. Now, the reason some of you might be saying 4 days. Well, we're not going straight there. We're going to get into orbit. We're going to hang out for a bit. We're going to go there. We're going to hang out in lunar orbit for a bit, and then we're going to land on the moon. Landing from launch takes about 4 days. So when we're talking about how many lunches to pack, that's so this is known as translunar insertion. We look at that trajectory. We get the delta V from orbit about 3.07 kilometers per second. So that's how much more energy we need to get to the moon. Y'all keep track of all these numbers, right? All right, here's the animation made by the fanciest computers of our day. Okay? A team of animators from Disney spent hours drawing this. So after about 3 days, now capture and release, that is when the force of the moon is stronger than the force of the Earth, and then vice versa when it is released. Force of the Earth is stronger. Now here, because I don't calculate air resistance, the spacecraft goes into the atmosphere, doesn't notice it all, whips around the Earth and keeps going and is basically accelerated into a solar orbit. But that's what we want right there. Look out, it looked like it almost hit the moon. Let's get a little bit closer here. And we'll go a little bit slower, but you can see how much we are accelerating now. Major U-turn from the moon's gravity. And now, after the release, we're going to start accelerating back to the Earth. If I go back here, just look how, well, we'll let that restart. I want you to notice how quickly you get halfway there, but then how slow it starts to go. So watch this here. It's going to reset, boom, with it. Okay, halfway there, and now really starting to slow down. And now right about here, it's going to accelerate. And if I even go back 2 slides here, you can see the first day, you're about halfway there. And then it takes another 2 days to get the rest of the way there. That's because you're slowing down. Because of the Earth's gravity. Yep. Uh-oh. There we go. All right, so we're getting pretty darn close to the moon. This is the flyby. But all right, now this is in the moon's frame of reference. It doesn't look as tight. This is what it looks like from the moon's perspective. You whiz in. Now we have some velocities here. We're flying past the moon. Again, we get our velocity of orbit that we're looking to get captured in. We have the velocity that the spacecraft is going, the velocity that the moon is going. We add those together. That's the delta that we're dealing with here. And that is, another great little fun fact for you. Because the moon is lighter than the Earth, it actually takes longer to orbit the moon than it does the Earth. About 90 minutes For Glenn to go around the Earth, it's going to take us 2 hours to go around the moon at a lower orbit. But yes, the lunar orbit insertion delta V 920, so 0.9 kilometers per second. Okay, so that's more delta V that we need to do this mission. Lunar descent, same thing that we did for getting into Earth orbit in reverse. We take these velocities, we add them together. I'm adding 10% because this is the one that really makes me nervous. I don't want to run out of fuel trying to land on the moon. So 1.9 kilometers per second for lunar descent. Okay. We're on the moon. We got 2 more burns to get home. We got to get off the lunar surface, and then we have to do a trans-Earth insertion to get back to the Earth. Those are the same burns that we just did, just in reverse. So another 1900 to get off the moon, another 920 to get home. And then luckily, the Earth is going to do the work for us. We don't have to do a slowdown maneuver. So, real quick, is this reasonable? Do we have engines that can do this? If I calculate a burn rate, it tells me that that rocket's going to have to burn for 2 weeks. That ain't going to do it. Okay, so here, 2 different equations. So the fuel rate of the rocket, the mass of the fuel, divide them, you got your burn time. There's a more complicated one. I got both of them here. They're pretty close. Take the average. These seem reasonable to me. I got like what? 3 minutes on the first stage? Sure, we can do that. Couple minutes on the second stage, no problem. Translunar insertion, couple minutes, no problem. Lunar orbit insertion, couple minutes, no problem. All right, we're good. All right, now that's the what. Now we need to do the how. This is a little bit more complicated. Those are the burns that have to happen. But there is a bunch of ways that you can put a spacecraft together and do those burns. So briefly, I'm going to try to cover 11 of them. We've got a lot more than I could have subjected you to. This is the big decision I'm going to have at the end. There's 4 main ways that we have that are in contention. Direct, Earth orbit rendezvous, lunar surface rendezvous, Earth orbit rendezvous, lunar surface rendezvous, and lunar orbit rendezvous. There's multiple of each of those, but 4 I want a decision on. So, direct, I got my model rockets. First stage, second stage, just get you into orbit. Third stage, just get you to the moon. We got this big boy right here. She's off to the moon. Okay. Oh, I went to staging too quickly. Well, I gotta fly to the moon. Why isn't it going back? There we go. All right. You don't have to worry about the numbers. The last one is the only one we're going to talk about. Here's my rocket. I won't say anything. Okay, now that lower stage used all of its fuel just to do that. Now, this guy comes back. Oh, that sucker's about 100 feet tall, weighs 150 tons. It's absolutely enormous. This rocket, so how we do this is we start with an estimate. $5,000 kilograms. Now tell me I'm wrong, all right? That's our payload. That's what I think is the minimum requirement to keep a human surviving for a week. Tank fuel total. You take that total, you put it as the beginning of the next stage. Tank fuel total. Boom. You take that as the beginning of your next stage. Tank fuel total. Next stage. Tank fuel. You see how these numbers are getting better? 4.4 million kilograms. Size of this rocket. Okay? So for this one, I'm just going to talk about the first stage, give you something to chew on. Weight, 4.4 million kilograms. Force of the rocket on the ground, 44,000 kilonewtons. Thrust of an F1 engine, call it 7,000 kilonewtons. Divide those numbers up, We need 6.5 just to balance the weight of the rocket. So you need about 8 of them to get the thrust to weight ratio up where this thing will actually get off the ground at any kind of useful speed. So 8 F1 engines is going to take at least a 15-meter diameter first stage. Now we look at the density of our fuels, combustion ratios, total fuel mass. I get a volume of liquid oxygen and RP1 propellant. Okay, I put that into a 15-meter, 50-foot for the Yankees, diameter tank. I get a fuel height for each, put them together, 20 meters, ends up being about 100 feet tall, 50 feet around, enormous. Do we have a facility big enough? Y'all in the government, you tell me. I know the answer. We don't. So we're going to have to build something. So this is when I open it up to comments from the distinguished guests. Any problems with this system that I've laid out here, this direct ascent trajectory, 4.4 million kilogram rocket? Does it sound like the way to do it? Simple. Build it and they will come. All right. Direct version 2, we can save a little bit of weight. I can get this thing down to a mere almost 4 million kilograms by combining lunar descent and lunar orbit insertion. Separate those. Make this yes. Now that's whole stack instead of this big which is this whole thing has to go. That means larger control, all kinds of weird stuff. Also, we got to jettison that in lunar orbit. We've spent 5 hours in space. So that could be a problem. All right. If you don't like that, I got another one for you. Earth orbit rendezvous. So we got 2 rockets. These first stages just get us into orbit. Then down over there we have lunar orbit insertion, and our ascent, and trans-Earth injection. So it is the same direct ascent. Instead of one big rocket, we break it up into 2 pieces. So basically, we send just that guy up, but basically empty. And we're going to refuel him with this guy here. Okay? We can do this 2 ways. We can develop one launch vehicle and build 2 of them. So same rocket, same tank, just got to build 2 of them. Some fuel there, some fuel there. We transfer the fuel in Earth orbit before we go. Never done it. Never even thought of it. But we can, what do you mean now? It's 1962. All right. Can I go back? Average weight of these 2 vehicles, less than, well, a little bit more than half of the direct. We're down to 2.4 million. More reasonable? But you gotta have 2 of them. So the total weight now is 5 million kilograms. 2 launches. We're only halfway confident in our Atlas rocket right now. The other way to do this. So the first way is what's called a connecting transfer. So we just send up the fuel, we send up that guy, the fuel stage attaches to that stage, and we shoot it over. The downside with this is these are very different rockets. So you need to develop 2 independent launch systems. That's all the calculations for this rocket, thrust to weight, engine performance, staging. Do it again. But everything's different because this rocket is different. It's a different mass, different payload. Do we have the time to develop 2 independent heavy launch systems when we ain't even done one? Fuel transfer. One rocket, simpler to design, but you got to do the fuel transfer. Lunar surface rendezvous. Here's a doozy. Instead of rendezvousing in Earth, where we got this complicated fuel transfer, what if we just send a lander and send a fuel depot to the moon before they even get there? So you got your fuel. Now you land your descent stage next to that fuel, pipe it on over. What could go wrong refueling an ascent module on the lunar surface? Astronauts, they can handle those pipes and plumbing just fine. Also, I don't know if any of you remember, but several of our Mercury flights have been several hundred miles off their landing sites. So if that lander doesn't land within the length of your hose, it's going to be a problem. However, look at these weights though. 1.7, 1.8 million kilograms. We're getting lighter. It's going to be doable. Now there is another way to do this. Have the astronauts leave in one craft, a lunar module, and then send an unmanned craft for the return module. That makes each of those capsules lighter because each of them only have to keep the astronauts alive for half the trip. So they're lighter. We get lighter rockets. But again, precision landing is crucial. Now, this also avoids the problem of fueling on the moon. You still have to make that landing. Now, instead of the length of the tube, it's how far can they walk. So they can probably walk farther than that like this. Finally, we got lunar orbit rendezvous. This is a pipe dream, folks. This ain't never gonna happen. Too complicated. First two stages, just get us into orbit. Translunar injection just gets us to the moon. And now we have two vehicles. One just goes down to the moon. Here. I gotta put this back. All right. So instead of this lander, it's big girl right here, I got itty bitty lander. All right. So I'm gonna take the upper stage from the direct ascent. I'm gonna marry it to this other small lander, and we're gonna boost both of these to the moon. I'll be back, y'all, on the moon. Once that moon is separated, it goes down.
140 windows all over.
And now these two have to find a way to get to the second place in space, a quarter of a million miles from Earth. Whatever the velocity was, a couple kilometers per second. Joining everything's in here. Okay, folks, we ain't been to the moon. We've never had two spacecraft in orbit at the same time. We've never gotten two spacecraft near each other at the same time. We don't know what happens when you touch two spacecraft at the same time. And now, I'm leaning toward, we got a German in the office. He really likes that direct ascent. It's starting to look better and better. Now, there are other ways to still do lunar orbit rendezvous. You can do an extended third stage the way we did with direct to save a little weight. You marry the lunar orbit insertion burn and the lunar translunar insertion burn, and you make your command service module a little lighter. Okay, but again, issues dumping that stage, larger RCS propellant load. Talk to the Grumman boys. Now, one that I really like, but didn't pan out at all, is the super command service module. What if it just did everything? What if it did a trans-lunar insertion, the lunar orbit insertion, and the trans-Earth injection? Okay, well, you crunch the numbers. It's way worse. 3 million kilograms. No, doesn't work. Yeah, I have that engine. You know what? That's a good point. I did not bring that up. That's another issue with some of these the engines that we're proposing using multiple flares. Now, this is called split lunar orbit rendezvous. You just cut the rocket in half and do everything separate. You still send both of these spacecraft to the moon. They marry up. They come back. This really lightens things up. But again, put those together, you're pretty much at 3 million kilograms. And you got 2 rockets that you got to launch windows, etc. Now, before I go for broke, opinions? What do you think the best way to do this is? Who likes direct? Big old rocket. One rocket. That's what he wanted. Until he got told about Earth orbit rendezvous. Now he's all Earth orbit rendezvous. Earth orbit rendezvous?
Yeah.
I'm going to fast forward to the future real quick. Does anyone know what Artemis is doing? Earth orbit rendezvous. Who likes lunar surface rendezvous, precision landing, walking home? No? Very much. Lunar orbit. Too much? Good enough? Pretty dangerous. I don't know. All right. So these are the decisions that you guys about because y'all have to build it. I build Geminis. I don't have to deal with none of this. But before we actually look at some other stuff, so far we focused on a small, lightweight, short duration lunar landing. A couple days max, 3, 4. Okay. What if we wanted 100 US ton payload on a fully reusable rocket in a 2-stage? Remember, direct was 5-stage, and that was about as simple as you could get. Lunar orbit rendezvous was like 8 stages and different burns and all kinds of crazy stuff. What would that look like? 2-stage. Keep it simple, people. Super heavy, fully reusable. We don't have to build a bunch of these, okay? I'm going to call this Astro Boat. Okay? This is what it's going to look like. Okay? This is the 2nd stage. See, okay? First stage here. 2nd stage here. Science fiction. This thing is definitely science fiction. I'm just having a lark with you guys. I ain't never going to build this thing. All right. So 30 feet across. You can see I got little humans in here. This upper stage will take 50 people to the moon. All right, let's look at the numbers here. Gross mass, about 5 million kilograms. So it's bigger than our direct rocket, right off the bat. It has our direct rocket just in fuel, and that's because you waste a lot of fuel being reusable. ISPs, you guys don't even worry about any of that, but what we're going to estimate 100 tons. All right, this thing, first stage, 3.5 kilometers per second, delta V. Upper stage, 7,000 kilometers per second, delta V. Gives us a total around 11. This thing gets to orbit and is essentially empty. That's the downside to 2 stages. So, how many to refuel to do the rest of our mission? It's about that many. About 12 to refuel. Okay? And I'm sugarcoating it because that's not enough. Okay? With one of these Astro boats in orbit, it's got 7.4 kilograms per second delta V. That's not enough for a lunar mission. We need at least 8.7. Okay? That's with minimal margins. So you need an additional 1.3 kilometers per second after you've left the lunar surface to get home. And remember, the second one that you sent out there, we want to get that one back too. So we're going to need another partial refuel in lunar orbit to get the sucker back, and we need about 8 more. So this is the fleet of rockets. Now remember, we don't need all of these. You can reuse them. So you might only have 4 of these, but it's got to go up, come back down, get refueled, go up, transfer its fuel, come back down, get refueled, go back up, transfer its fuel, come back down, get refueled, go back up. And we just rotate these. This is going to be easy.
This is 1962.
1962. This is for after Apollo. This is what we're going to do in the future. We're talking about putting a lunar base on the surface. So this is a side-by-side of a concept of our lunar lander from the Grumman boys. Lunar lander, 24 feet tall. This lady voter, second stage, 100 and some feet tall, 30 feet around. I'm sure that there's a flat spot on the moon somewhere we can park this boy. Here's next to a proposed in the circles I'm running, they're still calling it the C5 rocket, but they might end up calling it a Saturn or something like that. But that's C5. Nova's a C8. We got a C1 that we're using for unmanned flights. Taller than the C5. I don't know what this is. I don't know. Von Braun loves his space plane. He put that in there. How am I doing on time? I'm okay. So navigation, kind of out of order. I was going to skip this stuff if I needed to, but we can do this. We've been talking to our boys in orbit, but we have stations all over the globe. We still have a lot of dead spots, but when we get to the moon, it's gonna be easier because the overlaps become great. You're not gonna have right now when our boys fly over this part of Australia, there's a communication blackout. But when you're quarter of a million miles away, there's no more blackouts. So that'll be fine. We got a bunch of these. There is another way. We also do this with radio signals, but you can also do this with just measurements. You have two stations on the Earth. You look at the limb of the moon, background stars, you can triangulate the position of the moon. So now you know where the moon is. Your spacecraft is floating out there somewhere. There's only one solution that solves for these two angles. So you measure from the spacecraft to the moon and from the spacecraft to an edge of the sun or an edge of the Earth. Those two angles, there's only one place that those two angles put you at, and it's right there. So that's another way that we can do this. So if you know where the moon is and you tell your boys the moon's there and then they measure angles, they can figure out where they are. There's also some neat stuff when we fly behind the moon. There's a radio blackout because we don't have any communications on the far side of the moon. You know exactly when you should go into radio blackout. If you're within a second, the trajectory is probably good. Problem is, if you're wrong, by the time you know you're wrong, it's basically too late. The craft doesn't have the energy to miss the moon if it's gonna hit it. By the time you've done your calculations, and it's like, oh, we've got an intercept, it's too late. So that's the basic presentation. Give you something to chew on. If you have any questions about that goofy astro boat thing, talk to some people at the end. They'll tell you what I'm making fun of. But I wanted to show you guys that I'm not making this up, but the math does work out rather well. So this is the hindsight. I can take off my glasses now, 2024 again. Direct. So this is off of Wikipedia. Take that for what it's worth. But they listed the total mass of the Nova rocket was suspected. They never built it. 4.4 million kilograms. So I hit that within 1%. Okay. Fiddled it a little bit. If you look at the actual the dry mass of the different stages and the fuel masses, you can see, 59,000, 63,000, 11,000, 13,000. These aren't as good, 115, 106. But this comes down to where you decide to stage those rockets. You make the first stage a little smaller, the second stage a little bigger. You can get these differences. But the overall delta V requirement is physics. There is a absolute minimum if you're trying to land on the moon. A quick little side note, Von Braun and them, the original plan was not to go into lunar orbit. You guys remember the animation of the thing hooking around the moon, getting pretty darn close and going pretty darn fast? The idea was, instead of hooking around the moon, just go into orbit and then slow down. That's actually what they meant by direct. If the motor doesn't fire, you just impact the moon. Not the way to do it. It does save a little bit of fuel. So now, to give you guys, I'm going to spill the beans. what they ended up doing was lunar orbit rendezvous, the first of the lunar. They didn't do the split. They didn't do the extended. They didn't do the super command module. They said the bone stock lunar orbit rendezvous. If you were paying attention to the numbers, it was just under 3 kilograms. It's pretty good. So here's just the delta V's that I talked about, like those minimum amount of energy to go where you were trying to go. This is based on by the numbers. They have crazy data from Apollo. If you are a fiend and you want to know how much weight did Eugene Cernan lose on Apollo 17, it's in there. If you want to know what the weather was like when Apollo 13 launched, they've got so much just data, crazy amounts of data. So I've got the Apollo program average on the left, my estimate in the middle here, and then the error. So 2%, 8%, 10%. I call that pretty good. There are potential reasons for this. So in this lunar orbit insertion and translunar injection, I was doing 2D, folks. If you go 3D, where you're trying to go off axis and then hook around the moon to get to these lunar highlands, a little bit more fuel. So that might be why I'm under on some of these. The transit time, same thing. This one, there was limited data on. I only had 15, 16, and 17, but it's probably pretty good. So apparently, I'm overestimated. Weight. I was kind of just guessing, looking at things like, what makes sense? So I hit the total mass of the Saturn V rocket, 5% lighter. Again, I used minimal margins. Don't worry about the inner stages and stuff, but basically, I underestimated the command service module mass, and I grossly overestimated the mass of the lunar module. Good Lord, did they make that thing light. You're telling me the ascent stage, not the whole thing, but the little ascent stage on top of the lander, 2.1 thousand kilograms. It's nothing. It's nothing. 2,000 kilograms is 4,000 pounds. It's a decent SUV. And that thing, yes, that's dry weight. No fuel. Weight 6 times less on the moon, which if I go back to the that Astro boat thing, what it weighs on the moon and stuff, it's still pretty good. So yeah, you can build it crazy light, scary light. I thought I was being too light, and I was not. Burn times. So these are, but again, I didn't have great, and again, this can change based on how you're staging the particulars of what motors you're using. So yeah, I had my 2 times, I averaged them, I get these. Still, that's pretty decent. This 33% is only 8% if I remove those margins. And this is basically because of I made the lunar module too heavy. And if it's too heavy, you got to burn more to do the same thing. These are the 2 references that I really like. So this is Apollo by the numbers. It's a very dry read, but for a presentation like this, it was very nice to have because I could cheat and look at the answer. And then How Apollo Flew to the Moon is like one of my favorite books. This very much more digestible, but goes into the details of every system of Apollo. And so with that, I'll open it up to questions, comments, concerns. Yes, Diane.
Considering why these processes used by the Soviet counterparts,
They had some different ideas on things, but I don't actually know what the N1 was planning to do. Just lunar orbit? Oh, lunar orbit rendezvous? Yeah. Yeah. Oh, go back all the way.
But they did contemplate those projects you were interested in.
Yeah, and while I had to stop at some point. You can start, there's so many ways to skin this cat. You can start looking at, oh, well, I'm gonna transfer this, and then that's gonna. Another huge difference between how I simplified this and how they actually did it, if you're aware, let me go back a little bit further. The Saturn V was 3-stage to orbit. It was first stage, second stage, and then the third stage did a partial burn that got them into orbit, and then the rest of that stage did your translunar injection. I broke that up to make the work simpler for me. So this is where you get down into the weeds, because where you decide to stage those rockets can also like, you don't have to split these perfectly. I could have this part of this, and when we're 10 miles off the lunar surface, then we jettison this, and I'm going to use this for the absolute final stage of the thing. That was also considered. Yeah. But you get pigeonholed eventually, because you have to make a decision on these engines. So this is like, you may have also seen rockets that use 2 different engines. It's because 1 wasn't enough, 2 was too many, or 2 wasn't enough. So now we add 2 smaller rockets on the side, because say, we developed like 5, 6 rocket engines for this. So now you're just trying to figure out, where do you stage this thing to optimize a certain number of engines? And so you might get a situation like this where, this is fine for me to play with and say, hey, this saves a little bit of fuel. But if I actually do, and I find that this engine is not sufficient to push both of these at the same time, then 2 of those go out there. My tank to fuel ratio goes up. My efficiency goes down. I probably end up losing the mass benefit that I had. Complexity. I don't want to do that. I don't want to have to put 2 engines on that stage.
You imagine the heat of debates that must have gone on regarding reliability of the different systems.
So, while I was putting this together, the reason why I bought the tie and I made the laser pointer and all the stuff, I read an article about when all of this was going down, when they finally had the meeting. Von Braun surprised everyone and supported lunar orbit rendezvous, and then the whole framework around NASA shifted, because he went from Earth orbit rendezvous to lunar orbit rendezvous. At that point, there was kind of a small group of guys saying this is the way to do it. That was I think it's maybe a month or so ago, but it was 62. Right around now is when this stuff was happening. And it's wild to think about, because like I said, we've had 3 successful missions, 6 hours in space, but some of the hardware was, and yeah, heated debates. Talking about the Sea Dragon. Oh, they had concepts for rockets that were way bigger than the direct. I mean, they had concepts for things that were like 3, 4 times, 100-foot diameter first stages, just crazy. Man, maybe you can manufacture that stuff, but when I get my slide rule out here, nope, doesn't work. What was I was trying to go back to. One of the things that I'm almost surprised they didn't do, because it seems they could have done it. Apollo 8 actually orbited the moon. Come on, one more. This. It's shorter than some Gemini flights. It's only 8 days. 1, 2, 3, 4, 5, 6 days. So if we have a booster that we can dock the Gemini to, we can boost it on a free return. So you don't orbit the moon just one time around and come back. Well, we could do that in 1965. Little surprised it was suggested, but it never ended up happening. That'd be wild.
As I recall, the, one brother was a guy that finally got convinced because he was convinced that that was the only way we could meet Kennedy's.
Yeah. Yeah, so when you go back to those considerations, it might, Earth orbit might be the way to do it if you have the time to develop multiple heavy launch systems. We don't have the time, and we don't have the facilities to build the direct rocket, which was called Nova. So the only way it's going to happen, and von Braun was probably smart enough to know if it didn't happen, it wasn't going to happen. He just wanted it to happen. So yeah, he slowly became convinced that it wasn't the best way to go, but it was the way that was going to work in that short timeline of 1970. Gary?
As you said, for the reason we're making good contribution. Now, without using that analogy, around 18 years ago, I wrote a letter to the Chinese ambassador, and I said, without the Gemini reference, is that we need to do. Can you even you can send a man around the moon, and the humans will go crazy.
Yeah.
So the long-term strategic political, that I was thinking of. If the Chinese could hold a Gemini type thing, then I know the American mentality. And we are given to hysteria.
Mm-hmm.
I'm looking forward to it.
If they called it Sputnik 2, it'd be over. Well, we're just afraid of Sputnik. I mean, I'm also kind of surprised that we haven't seen that, because it is more doable than a lot of things. It's not it's 3 kilometers per second for boost, and then any of the corrective burns that you need to do are trivial. They're a few meters per second, maybe. You do one here, you do one here or here, and then you do 1 or 2 on the way back. Each of them at most a 1 second burn. I mean, that's what most Apollo stuff was. So the corrections are trivial. It's just the boost, and it's really not that much. It took you, give or take, 9 kilometers to get into orbit. You need 1/3 of that to get to the moon. So yeah, it's not the hardest thing to do in the world. Someone's going to call you out on not orbiting, but so another thing I didn't point out in the moment, but when we were doing the lunar surface rendezvous, when we had a separate fuel lander and then a craft landing, that fuel lander was tiny. It was only like 800,000 kilograms. And this shows how much heavier the rocket gets when you want to bring it home. You can get 100 tons to the moon for not much. You want to bring it home, you're out of your mind. And you want a fully reusable 2-stage rocket? There was another fun fact that I wrote down here, and so some of you may have caught it. Whoops, I'm going the wrong way. That direct 4 million kilograms, it's like 30 times the mass of the Atlas rocket, which was the only viable rocket we had at the time. So, there are meetings where people are proposing that we build a rocket that is 30 times larger than the one that they're currently using. And they're not getting laughed out of school. I mean, this is how gung-ho these engineers were about this. They thought they could pull that off. And the Saturn V is 20 times the mass of an Atlas. I mean, it's a big rocket. So kudos to those guys. Yeah.
I was thinking that how you talk about the compensation
that, I'm wondering if you have any idea what would comparison between the American and the Soviet, computer ability.
Oh, I'm talking completely out of school now, but probably more similar than you want to give them credit for. Once you get to a certain level, it's kind of all the same. But I would guess that we had some better stuff, but there were also some major differences in uh, how our economy was structured. They were trying to do things from almost a pure military. Everything was controlled by the Kremlin. We had all these contractors. So we had a huge group of people, and it's like, hey, get on making a suit, get on making a lander, get on making a second stage. And so they worked really well together, but they also had their own resources. And I've heard that that's one of the main reasons why we were successful is how we were able to mobilize a very diverse workforce for the same goal.
Computer design bureau, but kind of like.
Mhm.
So in many ways, is this the reason why we haven't done back to the moon? Give a quick explanation. Why?
Well, I mean, yeah, it's all dollars and cents. It's can you convince those government people in the back that there's a good reason to go? You know, Diane, what was the total budget of Apollo for several years? In the ballpark, in today's dollars, in 60s dollars.
We were after the time of 17, we were already had the next couple rockets and building them.
Mm-hmm.
But the American public lost interest.
Yeah. Yeah, I mean, yeah, I love moon rocks. I love science, but if I'm going to be completely honest, I mean, I want us to go back. I have zero faith in the Astro boat. I'm sorry, I don't think that is ever going to work and you don't have to take it from me. There's smarter people than me that have pointed out, and they said it takes even more stages than I said. I was being really nice to the Astro boat at 21. I've heard 24, I've heard 28, I've heard as low as 15, depends what you want to do. You can also not reuse all of them and save some stuff that way. You can also just deposit a 100-ton payload to the moon and get back for a lot less. But if you want to send 50 tourists to the moon and back, just the rocket to carry the people is going to be your 100-ton payload. You're not going to be depositing much on the moon. So you have to get that whole 100 tons of people and sandwiches and stuff back. I prove me wrong. I've been proved wrong before, but there's also intricacies in. So Apollo used a low retrograde orbit. Artemis is using a high Lisa Joule non-kinematic, some crazy word orbit, which is good from a delta V standpoint in some ways and terrifying in an emergency situation. So,
we were down here in the 60s. 60 miles below the surface is really new. Okay, Artemis is planning something more like a visit. And again, this is a 6-day orbit. Okay, so you're here, and now you're dying the ground says, oh, we're in trouble, we gotta come back immediately. And this is after this was 5 days for me to come back around. So,
I think the reason it's that is because it is so darn heavy. Doing a low retrograde orbit is too expensive from a fuel standpoint. You waste too much fuel getting that close to the moon like that. Again, there's many ways to skin this cat. There's dozens of orbital systems, and I started analyzing them, blah, blah, blah. It wasn't worth my time. But yeah, there's retrograde halo orbits, and there's these there's a bunch of ways you can do it, and they all have pros and cons. The con to the low is communication blackouts. You have to put a relay satellite in orbit. If you're visible, right next to basically the International Space Station for the moon, that's this guy going around. So if you guys are the Earth, and this is an orbit like this, and because of the weird interactions, that orbit is always going to point at you as the moon goes around. So you're not going to get into a situation like this. It's always facing you, just me. Communication. But that 6-day orbit just makes me nervous. I mean, you got guys on the ground that says, I got to come back now. And they say, no, can't. There isn't a launch window for 5 days. I don't understand. I've seen the discussions to blank faces of like, do we have an answer for this? And nobody seems to know. Yeah.
Well, this is an inherently dangerous proposition.
Sure.
There are lots of risks.
Lots.
And sooner or later, something's going to go wrong on people are stuck. And so, you have to balance safety versus other considerations.
But we're not beating anybody there. There's no gold. I want to go. Don't get me wrong. I can't make a good faith argument for why you need to send people to the lunar surface for long duration stays, the way that an International Space Station mission might be. I know that there's science to be had. It's just we're on the precipice of being able to send much lighter, more sophisticated rovers. I would love to be wrong. I want to go. The moon's way better than Mars. The view from the moon of the Earth, forget about it. Mars, just go to Arizona. It's the same thing. There's no reason. Now, from a propellant view, it's not actually much more expensive to get to Mars than it is to get to the moon. When we looked at those trajectories, you can hook around the moon, get slung out, and basically get to Mars for the same delta V that it costs to get to the moon. It's like if the moon's 3 kilometers per second, Mars might be 3.5, not even 3.2 something. It's just now you're coasting for that entire thing. But Mars has aero braking, so you don't have to do that burn to go into Mars orbit. However, the trip back up is way worse than the moon. So Mike O'Dowd did the presentation on the sample return. Send a rover the size of a car to Mars, pretty easy. Get 2 pounds of rocks back from Mars, virtually impossible. I mean, yes, we have the technology to do it, but the money, the expense is just crazy.
What I'm increasingly hearing people talk about is they don't want China to do it first.
And that's why they should, so that we do it. I want another space race. That's the only real reason. Yeah.
They're worried about China landing people in the
Yeah. Hey, if you're there,
and they're worried about China doing some kind of quick and dirty Mars, and just one scoopful of a bunch of dirt and get it back.
Good luck. Good luck. No, I mean
It's looking for improved proposals for how to get some of this stuff back.
Yeah.
In a hurry.
Yeah. And the way to do it in a hurry is to spend the money. I mean, that's all it is, but so little dark, right? Diane, tell me if I'm wrong. Had Kennedy not been assassinated, there's a good chance we were not going to the moon. Because if just a few things had gone a little worse than they did, at Gemini 8, those astronauts die instead of just barely being able to regain control of the spacecraft and come back to Earth safely. Funds dry up. But because Kennedy was assassinated, it invigorated the goal in a way. I mean, I wasn't there. Again, tell me if I'm wrong. Yeah. Yeah. Mhm. And they basically got a blank check after that. Make it happen.
We're all lucky Apollo 1 didn't ground.
Yeah. And had Kennedy not been assassinated and the political climate wasn't what it was, Apollo 1 might have been enough to be like, you know what, guys, this is getting out of hand. The Russians haven't done anything for years. By the time Gemini was closing, Russia had nothing for years, like 2 years, no launches. It's over, guys.
On the rocket, we didn't know that was the Russians were. They knew how they launched it.
Yeah.
They are trying.
Yeah.
In the competition.
But you could also make the argument, let them have. I mean, the reason that the moon was the goal, right, is because we got caught with our pants down. The Russians did a couple of things first, made us look bad. Our rockets were blowing up. Kennedy went to von Braun and the scientists, said, what can we beat them on? And they basically told him, any of these smaller milestones, you're not going to beat them because they're too far ahead. You have to do something crazy. So the moon was the only thing that we might be able to outpace them and get to the moon. But that's true. But it was more reasonable to think that they could pull off rendezvous and docking if they want. If that was the space race, right? Like no one's going to the moon. Yeah. Mm-hmm. I'm a simple boy from Louisiana that work on Gemini. I don't know the Soviet program. Yeah. Yeah, I mean, for my money, the craziest fact about the whole thing is that we did do it. I mean, everything tells you, just let them have it. You know, big deal. We did this other thing.
There's a bigger whisper to Space Force in the United States. You have anything to comment about that?
We should have a Space Force, but I mean, it kind of gets lampooned because of who started it and why they started it. And like, oh, the name's goofy. Air Force has the same name. You know, I mean, it's not a goofy name. It's Space Force. There's things to do in space. There's things that don't make sense to do in space. They've done both. So there's a big thing about hypersonics right now. I don't know. I mean, save the Earth. From who? I think Elon's trying to do that too. He wants to flip us off of it. All right, I'm getting the hook. No, I gotta be up at 5 in the morning, so I'll talk briefly with you all here and then I gotta go home. I'll put my cigarette out. Thank you.
All right, everybody. So that was. Thanks, Jeff.
I'll get out of here.
All right. So our next meeting is actually next week, Thursday, and then we have our open house at 25th, which is the fourth weekend. So with that, we are going to close this down. Thanks for coming, everyone. Good night. Oh, oh yes. If some of us are going to be going to the restaurant afterwards, the Red Coat Tavern, and